Alright, so I'd like to discuss relativity. And to do that, I first want to remind you of our Physics 130 descriptions of relativity. Our postulate 1, the laws of physics are the same in all inertial reference frames. Another fancy way of calling this is to say that things are covariant. What we mean by that is that the mathematical form of the physical law will remain unchanged. So let's start with our discussion of Galilean relativity. So recall in Galilean relativity we had an unprimed frame, we'll call it the S frame, with axes x, y, and z, and a second primed frame, I'll call it S prime, with axes x prime, y prime, and z prime, and the S prime frame is moving with velocity v with respect to the unprimed S frame. For convenience, I have chosen that the velocity of the S prime frame with respect to the S frame is purely along the x, or the x prime axis. Note that I've also snuck in that the x and x prime axes lie along the same axis. Right? Again, not necessary, but makes our life easier. So, also for convenience sake, I would like to throw in that that we're just going to assume that at t equals t prime equals 0 seconds, the two origins coincided, such that the origin in the unprimed frame and the origin in the primed frame coincided when their clocks t and t prime both read 0 seconds. And if we do that, we get the following. First, we get that sorry, I should have turned the notifications off. We get that x prime is equal to x minus vt. And so again, coming back to our little pictogram, that the coordinate in x prime is just equal to the coordinate in x minus v times t. So if I were just to pick some coordinate, the x value and the x prime value are related by this statement. And hopefully you can convince yourself that that is true. Since the velocity, the relative velocity of the two frames is purely chosen to be an x here, then y prime is y, z prime is z, and probably the one that you would have been certain of, t prime is t, right? If I take the first derivative with respect to time of both sides of these first three equations, well, the derivative of position with respect to time is our speed, right? And so I've already used v for the relative speed between the frames, and so I'm going to have to introduce another one, and this one I'm going to call u. So if I take the first derivative with respect to time of x prime, I'm going to get the speed ux prime. And similarly, the derivative of x with respect to t gives ux. The derivative of minus vt with respect to t is just minus v. Hopefully that's not terrible. For y prime and z prime, note that since there isn't this second term, it really just turns into uy is uy prime and uz is uz prime. Hopefully that's not terrible. What would happen if I took yet another derivative of these three with respect to time? Well, then I would get acceleration, right? And so ux minus v, the derivative of that with respect to t, remembering that v is constant, is just ax, and ux prime, first derivative with respect to t, would give ax prime. Similarly, uy and uy prime give ay and ay prime, uz and uz prime give az and az prime. The nice thing about this is, at least as far as covariance is concerned, one of our laws was that the sum of the forces is equal to the mass times the acceleration, right? The sum of the forces is equivalent to the product of mass and acceleration. Well, if we don't agree on the accelerations in s and s prime in our two frames, then how could we agree on the sum of the forces? Let's look at yet another one. This one's a little crazier, so forgive me. But let's, as far as covariance is concerned, let's look at whether or not momentum conserves. And so let's look at a pair of bodies, little m and big M. They have some earlier speed, respectively ux1 prime and ux2 prime for little m and big M respectively. They have earlier speeds. They also have later speeds, right? And so if the law of conservation of momentum is to hold, then it should also balance for the unprimed frame as well. So if we just sub in what we mean by ux1 prime and ux2 prime and ux1 prime later and ux2 prime later, the earlier and later cases, well, ux1 prime earlier is just going to be ux1 earlier minus v. Ux2 prime earlier is just going to be ux2 earlier minus v. Ux1 prime later is just going to be ux1 later minus v. And ux2 prime later is just going to be ux2 later minus v. But something really cool happens here, right? Is that we get a minus little mv, a minus big MV on the left side, and on the right side we also get a minus little mv and a minus big MV. And so I can add that to both sides and they cancel, yielding that mux1 earlier plus big M ux2 earlier is equal to m ux1 later plus, that should be a big M ux2 later. Hopefully that's all right. So let's carry this a little further. Sorry, my neighbors are doing some form of construction in their yard, so let me start again. So normally I would spend a great deal of time discussing the Michelson-Morley experiment in lecture. However, since we're delivering this remotely, and this is something that you can Google quite readily, I will leave you to that. The gist of it is we've spent a great deal of time talking about light as a wave. And one of the things that we've kind of glossed over is that waves require a medium. That was what we would have told you explicitly in the 1800s. but we know that light reaches us from the sun and other stars, and there's a whole lot of nothing between us and other galaxies, right? There's not a whole lot between us and the sun. The particle count is incredibly low per cubic centimeter, per whatever you want to look at. And so it was proposed to consider an ether that would permeate space. And the ether had to have some unique properties because we'd never noticed it before. It had to be something that we couldn't see, touch, taste, smell, or hear. Moreover, light needed to be able to be aware of it, right? Because it was the medium for light. Michelson and Morley had this really cool idea that that if they fired perpendicular rays of light, that they couldn't both be traveling through the ether in the rest frame, and so even if Earth is moving through the ether, by firing perpendicular rays, they were able to expect a difference in speed of light. They crowdsourced fancier and fancier versions of this experiment until eventually they got to the point where they were confident in a null result, meaning that they were confident they weren't going to observe a change in the speed of light. I encourage you to look up the details of the experiment, and by all means come to office hours virtually. So let's think of where this leads us then. Einstein wasn't alone in having this idea, but he definitely carried this through to a greater extent. And so let's go through Einstein's principles of relativity. So they seem somewhat innocuous at first. So the laws of physics must be the same in all inertial reference frames. In other words, the physics that we're teaching you in our classroom or wherever you happen to be watching this video at the moment shouldn't just be true there. It should be true universally, as long as you're in an inertial reference frame, and we'll preserve that for now. Otherwise we're wasting your time, right? That doesn't sound terrible. The second one I actually would argue is, somewhat tied up in the first. The second is that the speed of light in vacuum is observed to be the same in any inertial reference frame, regardless of the velocity of the observer or the velocity of the light source. I don't know whether or not, so definitely the Michelson-Morley experiment predates Einstein's publication. I don't know how aware of this he was, though. But that said, in Physics 230, you saw that Maxwell is able to derive the speed of light, right? And so the first statement, that the laws of physics must be the same in all inertial reference frames, I think, since you can derive the speed of light from some of our previous laws in physics, kind of implies that you shouldn't be surprised that the second one is true, right? So hopefully that's okay. This is kind of like the end user license agreement part of relativity. So hopefully you guys are okay with this. If not, speak up now. I'll give you a few seconds. I didn't hear any objections, so So this is one of those times where you have just given up a lot by signing off on this. The first thing that we'll go over is this relativity of simultaneity, and let's do this case by case. So let's imagine that there are two observers. We could let one of these be S and one of these be S prime. And I think I named that one S prime. S prime is riding along in a very, very fast-moving truck. And lightning strikes both the front and the back of this truck. The observer out here at the side of the road, watching this go by, sees both of these events occur simultaneously, sees the lightning strike both the front and the back of the truck simultaneously. And the way that this is observed is that the light from that event then travels to this unprimed observer, right? And the light from those events arrive at the observer at the same time, right? Because remember, up above, you agreed that the speed of light in vacuum is observed to be the same in all inertial reference frames, regardless of the velocity of the observer or the velocity of the light source. It's a really fast velocity, right? It's about 3 times 10 to the 8 meters per second, 300 million meters per second, 186,000 miles per second. Really, really, really fast, but not infinite, right? That's the key thing here. And so it takes time for the light to travel from our event to the observer. And the observer out of the truck sees both of those events arrive at the same time. Hopefully that's all right. Now I want to turn our attention to what would happen to the observer in the truck. So the observer in the truck does not see both rays arrive at the same time, right? Because the observer is actually moving towards this event and away from this event. And so if the observer out of the truck sees both events occur simultaneously, the observer inside the truck can't see both occur simultaneously. So right there is probably a huge difference from the way that that you conceive of the universe around you. You probably think that that two events that are simultaneous observed by one person must be simultaneous for every observer. And here is our first taste of where relativity is going to be a little weird. By accepting that there is a speed of light and that we're all going to agree on it, then lots of weird stuff is about to start to happen. And this is just the first piece. In our next video, we'll go over a couple of the other really, really bizarre consequences of what you guys have just accepted.